Good evening, my YouTube viewers. It's Crystal here, and I'm just here because I want to give you another code review. This code review is going to be on TensorFlow, and it's going to be decision forest and versus linear regression on the Abalone data set, but really it's random forest. I'll just say random forest. We'll just say that. And so basically, I have written this code because I'm working on TensorFlow, trying to learn TensorFlow. And I wrote the program in Google Colab. Google Colab is a very good program to use because it's free and it has a Jupyter notebook, and so you can write your code in a cell, and then the cell will show your output if you want to see the output. And so that's the great thing about Google Colab, and that's what I've written this program in, was Google Colab. So TensorFlow Decision Forest is not actually installed on Google Colab, so you will need to install it. So that's the first thing you need to do. And then after you have installed TensorFlow Decision Forest, you need to import all of your libraries. So you're going to import TensorFlow as TF, import TensorFlow Decision Forest as TFDF, because that's a separate library, import OS, which is operating system, import NumPy as NP, which is numerical computing, import pandas as PD, which creates data frames and it's data processing, import math, which is an inbuilt library in Python that performs mathematical computations, and OS is also an inbuilt library in Python. Import matplotlib.pyplot as PLT, and that's for your visualization, and import Seaborn as SCS, that's visualization with statistics. And you can see that we're on version 2-12 of TensorFlow, and as late as last week we were on 2-11. So the thing about TensorFlow is it's always going through these modifications, and because it's always going through these modifications, that means some of the code gets deprecated. So that's one thing that you need to know about TensorFlow. So you have to stay abreast of what's going on with TensorFlow. One thing that I do think that the reason why TensorFlow has given you this decision forest, TensorFlow decision forest, is because you get random forest and gradient boosted trees in it. And basically what you get is, I think what they want to do is they want to give a replacement for sklearn. So they want to do a lot of the things that sklearn does, because, and I also wanted to say that I've imported sklearn into the program as well, but I import it when I need it. But they want to replace sklearn in their coding, but I went ahead and put some sklearn in there. So because I learned sklearn before I started learning TensorFlow, so I have put some sklearn code in there because it's easier for me to work with than this long code that you get with TensorFlow. And so I think TensorFlow wants to replace sklearn in their code, but I'm using it anyway. And if you go to a job interview, then it will hold you in good stead if you say that you know sklearn as well, So, and the thing about random forest is, whenever I was doing my research about TensorFlow's random forest, is they said that it was modeled after sklearn. And one thing that I didn't do in my last code review was I used random forest to check random forest out against TensorFlow and sklearn, and it had exactly the same accuracy on a classification, multi-class classification. And then I used gradient boosted trees with gradient boosting classifier, and that had the same accuracy as well. So I think that TensorFlow wants to model their random forest, will definitely model their random forest after sklearns, and possibly model their gradient boosted trees after sklearn. So to make these functions available, so you don't have to use sklearn if you don't want to. And then there's ways of getting around like some of the things that they do, such as train test split, but I decided to go ahead and use train test split because it was a simpler code to use than what they were using. So after we've imported our library, we're going to load our data set, and we're going to use the Abalone data set, which is an inbuilt TensorFlow data set, and that's what we're going to use. And so we're going to call it dataset DF. So you can see this is dataset TF. So you've got type is MFI. I'm not sure exactly what MFI stands for, but that's your type. You got longest shell, diameter, height, whole weight, shackled weight, visceral weight, shell weight, and then rings, and that's how many rings it has. And then I'm supposing, I don't know very much about shells, but I'm supposing the number of rings is indicative of the age of the shell. And you've got 4177 rows by 9 columns. And I just wanted to analyze the data set, so we check info, and you see that you've got one object column, which is the first column, and the rest of them are numeric. Do you want to check for any null values? There are no null values, so that's good. So we do not have to delete or impute any rows that have null values. So that's good. Now what I'm going to do is I'm going to analyze the data set. So I created a disk plot of, which I should have done this, but I didn't. That we created a disk plot of the rings, and then you can see that it skewed a little bit to the right, I believe. So that's the distribution that the rings makes. And then if I did the KDE equals true, you would actually get like a little line across the graph, and it would tell you the distribution that it makes. But I forgot to do KDE, which is true because I've been working on this most of the day. And then what we're going to do is we're going to do a value counts, and we're going to see how many rows the rings appears only once. And those rows that the rings appear only once, what we're going to do is we're going to filter them out. So is multi equals data df rings dot value counts greater than 1. Filtered equals dataset df rings dot is multi dot index. Dataset df equals filtered, and then dataset df, and you can see now we only have 4172 rows by 9 columns. So I think it was 5 columns that it dropped. Yeah, 5 columns that it dropped. Because the thing is that if you have an example where there's only one value of a target, then the model is not going to be able to predict on it because it doesn't have another one to predict on. So it's better to just remove it. And it did actually improve my error when I removed it. So now what we're going to do is we're going to do this plot of the type, and that's your MFI. I forgot to do the KD equals true, but that would just give you a little line right here to show you the distribution that it makes. And so MFI is pretty close. I mean, we're not going to say exactly the same, but roughly the same. So now what I did was I created a box plot of the type versus the rings. So you can see that I has the lowest amount of rings, and M and F are pretty much the same. Now what we're going to do is we're going to encode type, because when we go to encode the type, because it is an object, the model won't be able to make predictions on that column. So what we have to do is I replaced M with 1, F with 2, and I is 3. And so you can see here, we look at the data set again, and so rather than the type being MFI, it's now 1, 2, 3. So I created a heat map. You can see in this heat map that most of the columns are very highly correlated. And because most of the columns are very highly correlated, you could remove some columns. And so you can see here, but what I did was I did actually decide to remove some columns. And so rather than 9 or 8 columns, we were having rather than 9 or 8 columns, we were having maybe 4 or 5, something like that. But I noticed that it made the error increase. And since it made the error increase, then what I did, and again, NP bool is deprecated. It's just supposed to be bool. And what I did was I decided to leave in the columns that had a high correlation. So over here, you can set it up over here for 1, so it's not going to get any higher than 1. And the reason why it's not going to get any higher than 1 because it's 100%. But you could have set it up for 0.9, which is 90%, or 0.95, which is 95%. But since I noticed that the noise increased when I dropped columns, I just left it in there at 100%. So now you can see that this is exactly the same. We didn't drop any columns because it was 100%. So now what we're going to do is we're going to use sklearn to split the data set into training and testing sets. So train DSPD, test DSPD equals train test split, data set DF, test size equals 20, random state equals 42, and then you check your shape of train DSPD and test DSPD, and you notice both of them have 9 columns. And so now what we do is we set up our X train and our Y train. So X train equals train dfpd.ilog, and that means all of the rows and all of the columns except the last one. And Y train equals train.dspd.ilog, and that's only the last column that it uses. And then so X train equals NP array X train, Y train equals NP array Y train, and then we use exactly the same code for the test set, but instead of X train Y train, we use X test Y test. And then we check the shapes of X train, X test, Y train, Y test. And so you can see X train, X test has 8 columns, and Y train, Y test is a series, and it only has one column, but it doesn't even say 1. So now what we're going to do is we're going to create the TensorFlow dataset, which you're going to need to do for the random forest and the gradient boosted trees. So train ds equals tfdf.keras.pd data frame to tf dataset, train dspd, label equals label, task equals tfds.keras.task.regression. And we use exactly the same code for test. And now we use random forest. So model equals, this is defining our model. Model equals tfds.keras.random forest model. Task equals tfds.keras.task.regression. And then model.fit train ds. So that way you are training the model. And then we compile the model. We use the metrics as MSC, that's mean squared error. Evaluation equals model.evaluate. Test ds return dict equals true. We print our evaluation. Then you print a blank space. And then you print your MSC, which is 4.7, and your RMSC, which is the square root of the MSC, which is 2.16. And now what we're going to do is we're going to predict on the test set. So ypred equals model.predict test ds. Ypred equals ypred.astype int. And then ypred. So now you can see ypred. Here's all your predictions. And then we're going to use code that I developed myself to get the RMSC. And it's 2.27. That's your RMSC is 2.27. And you can see that the RMSC on the code that I developed is higher than the TensorFlow code. But I would go ahead and go with the code that I developed anyway. And then so we create a data frame. So you can see the data frame. And you can compare the actual values to the predicted values. Now we're going to use gradient boosted trees. Model 1 equals tfds.keras.gradient boosted trees model. Task equals tfds.keras.task.regression. Model 1.fitDS. So we're training the model. And then we're going to set up compile the model. Model 1.compile matrix equals MSC. And then we're going to evaluate the model. Evaluation equals model 1.evaluate test ds return dict equals true. So print evaluation, then print break line, and then you're going to print your MSC, which is your mean squared error, and then you're going to print your RMSC, which is the square root of the mean squared error. And so you can see the RMSC is 2.18, but let's look and see what it was on random forest. On random forest it was 2.16. So the error in random forest is less than the error in gradient boosted trees. And now what we do is we just create a data frame so you can check out the actual files, actual values against the predicted values. So now what we're going to do is we're going to check linear regression, because you can do linear regression in TensorFlow as well. So TensorFlow does a lot more than just neural networks, it does linear regressions too. So normalizer, that's where we're going to standardize our data. And when we standardize the data, it finds the mean and the standard deviation of a column, and then it standardizes it using the mean and the standard deviation. And so normalizer equals tf.keras.layers.normalization axis equals -1. And then you have to use the adapt function. So normalizer.adapt xtrain. So that's what we're using now, xtrain. So we print normalizer.mean.numpy, and then gives you the mean of every column. And it says first, this is the first row, and then it gives you what the first row would look like without normalization, and what the first row looks like with normalization. So you can see that. And now we're going to set up our linear regression. So from TensorFlow we import Keras. From TensorFlow.Keras import layers. So linear model equals tf.keras.sequential. Sequential is a model where you just have one layer after the other. And then we're going to normalize her is going to be, let's see what we've done here. Normalizer is going to be our first layer, and then after the first layer you're going to have one dense layer. And now linear model.layers 1.kernel, so that just gives you some information, which I'm not sure exactly what that is. I'll have to look it up. And then we compile our data, linear model.compile, optimizer equals tf.keras.optimizers.atom, learning rate equals 0.1, loss equals mean absolute error. And then so now what we're going to do is we're going to train the data. So from keras.callbacks import model checkpoint, comma, early stopping. Early stopping equals early stopping, brackets, monitor equals valve loss, mode equals min, patience equals 25, verbose equals 1, MC equals model checkpoint, brackets, best model.h5, monitor equals valve loss, mode equals min, save best only equals true. And then now what we're going to do is we're going to train the data. So history equals linear model.fit, xtrain, ytrain, epochs equals 100, verbose equals 1, validation data equals xtest, ytest, callbacks are early stopping and MC. So we train the data, goes all the way to 87, and then it stops because we've got it set up for early stopping. And then now what we do is we develop a plot of the validation, the loss for the train set against the loss for the validation set, and you can see that the loss for the validation set is greater in the beginning than it is for the train set. So now we're going to do test results. So test results, we create a dictionary. Test results linear model equals linear model.evaluate, xtest, comma, ytest, verbose equals 0. Then test results are 1.580. Not sure exactly what that means. I'll have to look it up. And then we do our prediction. ypred2 equals linear model.predict xtest. ypred2 equals ypred2.s.int. ypred2, so you can see your predictions. And then we use code that I developed, and we get an RMSC of 2.55. So you can see that the RMSC in linear regression is higher than the RMSC in random forest and gradient boosted trees. And then what we do is we create a data frame that gives you the actual values and the prediction values, so you can see how well you did. And so that's basically how it works. And so I'm still learning TensorFlow. So some of the things I'm still don't know very well. But I'm learning it, and I will pick it up as I learn TensorFlow. So that's it pretty much for this particular code review. I've covered the code for the Abalone dataset, which is a regression model, and we used random forest, and we used gradient boosted trees, and we used linear regression, and we found out that random forest performed the best, gradient boosted trees performed the second best, and linear regression performed the third best. So if you wanted to select a model to use, then random forest in this instance would be the best model for you to use. And so that covers it for the code review. I hope you like it. If you like my video, please like, subscribe, and share. Thank you so much to my subscribers for supporting my channel. And thank you for watching my video. I look forward to making more code reviews for you in the future.